So in this video, we're going to do an example of an application problem using a sum or difference angle formula, either sine or cosine. We'll figure that out as we go along. I'm not going to test you on this, so don't worry too much. This is a complicated problem with a lot of steps, but I want to illustrate here's why we need this formula so we can manipulate things algebraically using identities. We can't always just throw things into a calculator. Sometimes that works, sometimes it doesn't. And then at some point, you might be tasked with designing the calculator, so you have to know what's going on under the hood. So let's say we have what's called a simple coupled oscillator. So let's say we have, get the highlighter here. So we have this mass here, and it's a pendulum, so it's swinging back and forth, right? Now connected to it is another mass, connected at the bottom of it to the first mass. It's not also connected to the ceiling. This pendulum's connected to the first one, and it's swinging back and forth. And you can imagine what that might look like. I'll probably link a video in the description of here's what it looks like in action. Here's what this kind of thing behaves like, so you get a good visual of it. But for now, we'll just go with the description, right? So these two pendulums hang from a ceiling, one connected to the other. And let's suppose that the distance from the bottom mass to the wall is given by this function, p of t equals the square root of 2 times sine of t plus the square root of 3 times cosine of t plus 5. Okay, it's a formula that gives that distance as a function of time. T is in seconds, and the position is measured in centimeters. Okay, so what if we wanted to know at what times, maybe happens more than once, in the interval 0 to t, so 0 to 10 seconds, is p of t equal to 4? So if we wanted to know, say, p of 0, right, what is the distance from the wall at time equals 0? Well, I would just throw 0 in for t in both of those cases, right? You have sine of 0 and then cosine of 0. Sine of 0 is 0, so this whole term wouldn't matter. But cosine of 0 is 1, so you'd have root 3 plus 5 as a decimal. That's about 6.7. So that would mean when t equals 0, at time 0, the distance is about 6.7 centimeters. Okay? But what if I care about, well, when is this for? Do I want to start guessing at numbers? Guess a number, plug it in, guess a number, plug it in? Because then also, say I find a result. I get a number that when you plug it in, you get 4 as a result. How do I know that's the only one? How do I find all of them? So that's going to be really time consuming. We could do it by guessing, but how would we know when we're finished? How would we know that we found all the solutions? So instead what we'll do is we will solve an equation to find out when that occurs. So I'm going to set this function equal to 0 to find, I'm sorry, not 0, 4 rather, equal to 4 to find out when is the distance equal to 4. So we'll say root 2 times sine of t plus root 3 times cosine of t plus 5 equals 4. Okay, so we need to solve this equation for t. Now, this is not quadratic in form. We've had in previous videos an example where, say, cosine was squared, right? We'd have something sine t plus something times cosine squared of t, which means it's quadratic in form, and we can do a substitution, and then we can use a quadratic formula and solve that way. That's not going to work here. We're going to do something quite different. This is linear in form. There's no squared anything. To start with, I'm going to subtract 5 on both sides. So I'll have root 2 times sine t plus root 3 times cosine t equals negative 1. Okay. Now, what we're going to have to do is basically we're going to have to be very clever and do things in a roundabout way. This concept, part of the reason we're doing this example is this concept shows up again in Cal 1 and in differential equations. So this is something you're going to see again later. What I need to do is I need to think of, I basically pick sine or cosine. It doesn't really matter which I pick. I'll go with a sine to start with. Sine of some angle theta times sine of t plus cosine of some angle theta, which we will end up finding. We don't have it yet, but we will find it, times cosine of t equals negative 1. The reason we can do that is that this is then a difference angle formula for cosine. This is cosine of t minus theta. And that's going to enable us to compress this left-hand side into a single trig function and get our answer that way. So what we have to do is say, well, this sine theta, this needs to be some y over r. Oh, let me change colors again. Some y over r, and this cosine needs to be some x over r for it to be a sine and cosine value respectively. So I have to take the original equation, and I have to suppose, oh, this guy here, that root 2 is some y value, and this root 3, this is some x value. And I have to use the Pythagorean theorem, x squared plus y squared equals r squared, and plug those numbers in. So x squared will be 3, and y squared will be 2, of course. So r squared is 5. In other words, r is the square root of 5. And that's going to be very important for solving this problem, as you'll see in a second. So I'm going to rewrite the equation from a few lines up before I started modifying things with blue. And kind of don't want that to be curved. Don't want that to be straight, rather. I want that to be a curved line. There we go. Okay, so the square root of 2 times sine t plus the square root of 3 times cosine t, that equals -1. Now what I'm going to do is I'm going to divide both sides by the square root of 5. That seems like it's coming out of nowhere. I mean, I've partially explained it. I want to get these formats, y over r and x over r. Think of this as being, if you might recall completing the square from an algebra class, where you had to take this term, take a coefficient, cut it in half, square it, and add it to both sides of an equation to solve a quadratic using completing the square. And that step was really obscure. It ended up working, but while you're doing it, it might seem like it comes from nowhere. This is kind of similar, where it's not clear where this is going. I've said where it's going to go, but it's not clear yet. So just stick with it. It'll be fine. So I need to rewrite this a little bit. Whenever you have a fraction, like say 2/3, my mistake, 2 times 3 over 5, this is the same as 2/5 times 3. That 3 can be in the numerator or off to the side as a multiplier, either one, right? So I'm going to do that with each of these terms. I'm going to write this as root 2 over root 5 times sine of t plus root 3 over root 5 times cosine of t. And this all equals -1 over root 5. So now, this root 2 over root 5 and this root 3 over root 5, these are both trig values of some angle. Okay, root 2 over root 5, that is sine of theta, whatever theta is, I don't know. And root 3 over root 5, that is cosine of theta. Whatever theta is, we don't know it yet, but we will find it. So this is sine theta times sine t plus cosine theta times cosine t, which is -1 over root 5. Okay. Now, as I said, this matches one of the difference angle formulas. This is cosine of t minus theta. Okay. So we're solving an interval 0 to 10, which we'll get to in a second. But I can say, oh, well, then this means that t minus theta, right? This is going to be cosine, cosine inverse of -1 over root 5, or, if you use the symmetries of the cosine function, negative cosine inverse of -1 over root 5. So two possibilities, okay? There's we hope, quadrant 1 value and a quadrant 2 angle value that have the same cosine value. That's what we should be expecting, right? This one is a quadrant 1 angle. This one's a quadrant 4 angle because we've negated it. But we don't have t by itself. I really need to add theta to both sides. So t equals, well, each of these two possibilities, cosine inverse of -1 over root 5, which we'll get decimals for this later, plus theta, or negative cosine inverse of -1 over root 5 plus theta. Okay, And then we'll have to also consider the period, because t is in the interval 0 to 10 inclusive, right? So we're going to have to use the period of the cosine function to get the other values. There may be more, but there's this pesky theta. We don't have a number for theta, and we kind of need that at this point. So here's what we'll do. I'm going to say that since that's what we did here, let's do sine. Yeah, sine theta equals root 2 over root 5. And we really only need one version, although there are lots of angles that would satisfy this because of the period of sine. We only need one of them. The periodic nature we'll take care of a little bit later. So we're going to pick one. Let's say theta, the one we're going to use. This is equal to sine inverse of root 2 over 5. Right? When you have a root divided by a root, you just have the root of the fraction. That's the same thing. So that's what I can plug in here. I can say, well, this equals, I need a little bit more space because we're going to have to start thinking about the period. Cosine, make that a little bit neater, more neatly. Cosine inverse of negative 1 over root 5 plus sine inverse of the square root of, not 5 on top, sorry, 2 over 5. Plus, well, we're going to have the period, and we're going to have to check how many copies of that we need after we have a decimal approximation for this expression here. We might have to add 2 pi once to use the period to get other solutions. But then also, negative cosine inverse of negative 1 over root 5, root 5 plus sine inverse of root 2 over 5. Let me write that a little bit more neatly. There we go. Plus 2 pi k, however many copies of the period we need. Now, I thought I had a calculator handy here somewhere. I must have moved it because I don't see it. That's okay. I'll just use an online calculator. That's fine. Take me a second to pull it up. Okay, so I need cosine inverse of negative 1 over root 5. Okay, that's about 2.03, but I want to add to that sine of root 2/5. Okay, so I get, I'm assuming this is correct. I haven't confirmed it by double checking in 2 calculators, but I'm getting that this is approximately 2.719. Plus, we'll see how many copies of 2 pi k we need. And then also I need to negate that first inverse cosine. My other value is negative 1.350 plus 2 pi k, however many copies we need. Now notice that, let's keep that visible, notice that this 2.719 is in the interval 0 to 10, so we get one of our numbers. That is one point in time where the distance will be 4, 2.719 seconds. But this one is not. So that's not really one of our solutions. We have to add a copy of 2 pi to get our solution. Then also, remember 2 pi is roughly 6.3. If I add 6.3 to this, I'm going to get another value. It's going to be roughly 9. If I add 6.3 to this twice, I'm going to get a value greater than 10. So here's what we have. I'm adding 2 pi as needed. We've got, well, I guess I can drop that for now. So 2.719, that's one of our solutions. If I add 2 pi to that, let's do this. I'm going to get 9.002, almost exactly 9. Oops. Okay, that's for the top category, I suppose. Now, the bottom one, if I negate that, I'm going to get 4.933. That's from adding 2 pi once, because the negative 1.350 is not one of our solutions. We have to add 2 pi to get the first one. If I add 2 pi again, I'm going to get something greater than 10. So basically, I can just move this up here, add that to the end of my list, these are the values that t can take on in order for the distance to be 4 centimeters. So this is a long process. I wish I could show the 2 pages side by side, but you can see the first, just the description of the problem took up half a page. We got started with the algebra involved that we needed, and then we used the difference angle formula for cosine, and then we had to do some manipulations using inverse trig functions and think about the period of cosine in order to get our resulting values. So these are the points in time when the distance will be 4, which as an engineer or chemistry, physics, those different disciplines, this is the kind of thing you might need to solve from time to time, and especially the concept right here of rearranging something to simplify the left-hand side by supposing, well, what if this is a sine value and this is a cosine value? That kind of thing will show up again later in differential equations for those of you who are going to take that.